In this lecture, we would look into another important characteristic of a single mode optical fiber, and that is waveguide dispersion. We have seen that in a multimode fiber, if it is a step index multimode fiber, then the data rate is limited by what is known as intermodal dispersion, which is due to different modes carrying light into the fiber, and these different modes travel with different velocities. They have different propagation constants that gives rise to what we call as intermodal dispersion. We can minimize intermodal dispersion in a multimode fiber by having a graded index profile, and then in such a fiber we have intermodal dispersion, which is very small, and then another kind of dispersion comes into picture, which is known as material dispersion, which is nothing but the wavelength dependence of the refractive index of the material of the fiber. So, in a graded index multimode fiber, we have seen that the material dispersion and intermodal dispersion can become comparable. So, we will have to take into account material dispersion as well as intermodal dispersion, while in a multimode step index fiber, intermodal dispersion is so large that we ignore material dispersion. Although by using a graded index fiber we can minimize intermodal dispersion, but we cannot completely get rid of it. So, the obvious way to get rid of intermodal dispersion is to use a single mode fiber. Then in a single mode fiber, material dispersion would always be there, because the refractive index of the material would always depend upon the wavelength of light, and we are using a light source which always has finite spectral width. So, all the wavelength components will contribute. Then apart from this material dispersion, a single mode fiber also exhibits another kind of dispersion, which is known as waveguide dispersion. What is this waveguide dispersion? Because we have finite line width of the source, so different wavelength components of the source have different propagation constants of modes. So, in a way, each wavelength component has its own mode, and that mode propagates with different velocity. It has different propagation constant, and that gives rise to what is known as waveguide dispersion. We call it waveguide dispersion because it is purely due to the wave guidance in a fiber, because wave guidance in a fiber is different for different wavelengths. So, if I look at single mode fiber, then it supports LP01 mode, and if I plot its BV curve, BV diagram, then it goes like this, and I know B is related to propagation constant like this, and V is related to the wavelength like this. So, propagation constant depends upon lambda, and this relationship between the propagation constant and lambda can be obtained from the relation between B and V. So, for a given fiber, the propagation constant beta of the mode depends upon lambda naught, and this gives rise to what is known as waveguide dispersion. So, what I can do now, I can obtain the propagation constant of the mode in terms of fiber parameter and the normalized propagation constant B. How to find out the broadening of pulse due to this? So, the idea is exactly the same, the procedure is exactly the same as we had done in the case of material dispersion. In case of material dispersion, we considered optical waves propagating in infinitely extended medium, that is in bulk medium. So, we considered plane waves, and what we had done, if you remember, that in a bulk medium, the plane waves go like this. E is equal to E0, which is a constant, e to the power I omega t minus kz, where k is the propagation constant. E0 is constant, this is a plane wave, and k can be written as omega by c times n, and since n depends on frequency or wavelength, k also depend upon frequency. So this is a function of omega, and so this is a function of omega. And I know that if there is a group of waves, if there is a pulse, then the group velocity can be given by 1 over Vg is equal to dk over d omega. And that is how we obtained the group velocity and then transit time and subsequently the material dispersion. In case of optical fiber, what I don't have plane waves, but I have modes. And these modes propagate as psi r phi is equal to, let me put psi 0 e to the power I omega t minus beta z, okay, and this is a function of r and phi both. This is not a constant, this is a function of r and phi. Then instead of having k, I have beta, which is the propagation constant, and if I want to now find out the pulse broadening, then again I will have to find out the group velocity, and in this case the group velocity will be given by d beta over d omega, and this beta is a function of lambda naught or the frequency omega, okay. So the procedure would exactly be the same. So that is why I have written beta in terms of this, and since b depends upon v, which subsequently is a function of lambda or omega, so that is how I can now find out d beta over d omega. So if I look at this I have obtained for a weakly guiding fiber, because if you look into it, b is equal to beta square over k naught square minus n2 square divided by n1 square minus n2 square. So this I can approximate by beta over k naught minus n2 over n1 minus n2 for a weakly guiding fiber where n1 is very close to n2. So if I look at this expression, then even if the refractive indices of the materials of the core and cladding do not depend upon lambda, we would still have dispersion due to dependence of beta over lambda or dependence of n effective over lambda. So to calculate the dispersion, we will follow exactly the same procedure as we had done for material dispersion, and then in this way I will find out the group velocity by d beta over d omega and subsequently the pulse broadening and waveguide dispersion coefficient. So I again write down the expression for beta, which is 2 pi over lambda naught, which is nothing but k naught, n2 plus b times n1 minus n2, and this I can write as omega by c times n2 plus b times n1 minus n2, and if Vg is the group velocity, then 1 over Vg is equal to d beta over d omega. So I do d beta over d omega from here, so I will get 1 over c n2 plus b n1 minus n2 plus omega by c, then the differential of this would be 0, and if I take the differential of this, then it would be omega by c n1 minus n2 dB over dV times dV over d omega. So, please pay attention here that I have ignored here the material dispersion. I have assumed that n1 and n2 do not depend upon omega in order to isolate the effect of waveguide dispersion. So, in order to purely find out the effect of waveguide dispersion, or to purely find out the waveguide dispersion, I have assumed n1 and n2 to be constant with respect to omega. So, what is dV over d omega? I have V is equal to 2 pi over lambda naught times A times n1 square minus n2 square, which is nothing but omega by c times A times square root of n1 square minus n2 square. So, dV over d omega would simply be V over omega. So, I put it there, then I will get 1 over Vg is equal to 1 over c n2 plus n1 minus n2 times B plus 1 over c n1 minus n2 times V times dB over dV. So, now I simply rearrange the terms here. So, I take this n2 by c here and n1 minus n2 by c here, which I take common from this term also. So, here I have in the square brackets B, which is coming from here, plus V times dB over dV. Okay. So, this I can simply write as n2 by c plus n1 minus n2 by c, and this I can write as d of bv over dv, right. Now, I take n2 by c common, and then I can write it as n2 by c times 1 plus n1 minus n2 over n2 dbv over dv, and this I can approximate by delta. For a weakly guiding fiber, delta is n1 minus n2 over n1 or n1 minus n2 over n2, okay, because it is weakly guiding fiber. So, I can approximate it by this. So, 1 over Vg becomes this much. Once I have Vg, then I can find out what would be the time taken by pulse to traverse length L of the fiber, and that would be given by L by Vg, which is equal to Ln2 by C 1 plus delta d Bv over dV. Now, if I have a source of spectral width delta lambda naught, then the broadening would be given by due to waveguide dispersion, delta tau w is equal to d tau over d lambda naught times delta lambda naught, and tau is this much from the previous slide. So, if I just take d tau over d lambda naught from here, so what I will get Ln2 by C times delta times d2 bv over dv square times dv over d lambda naught times delta lambda naught, which comes from here. What is dv over d lambda naught? We know V is equal to, if you write back the expression for V, then V is equal to 2 pi over lambda naught times A times square root of n1 square minus n2 square. So, if you do dV over d lambda naught from here, you will get it as minus V over lambda naught. So, if I substitute it there, then I get the pulse broadening delta tau w as minus delta Ln2 over C lambda naught times V d2 bv over dv square times delta lambda naught. As usual, I define the dispersion coefficient as broadening per kilometer length of the fiber per nanometer spectral width of the source. So, dw is delta tau w over L delta lambda naught. So, it would be minus delta n2 by C lambda naught times V d2 bv over dv square. So, I have got this waveguide dispersion coefficient now. I can convert it into or express it into picoseconds per kilometer nanometers. So, what I do, I put C, the value of C here, which is 3 into 10 to the power 8 meters per second, and so if now if I put lambda naught in nanometers, then the dimensions of this would be seconds per meter nanometer, and this would be 10 to the power 12 picoseconds. This meter I can convert into kilometers and I retain this nanometers. So, it will become minus delta times n2 by 3 lambda naught times 10 to the power 7 times V d2 bV over dV square in picoseconds per kilometer nanometer, where lambda naught should be put in nanometers. So, what I see clearly that if I want to find out the waveguide dispersion of a given fiber, then I need to calculate this term V times d2 bV over dV square and then multiply it by fiber parameters n2 and delta, and of course divided by the wavelength, central wavelength of the pulse. So, I know how B varies with V for a single mode fiber. So, if I draw that, then the variation of B with V goes something like this. Then what I can do, I can find out first, because I need to find out the second derivative of BV. So, first I find out the first derivative of BV, which is dBV over dV, which goes like this, and then I find out d2 bV over dV square times V, which comes out like this. So, what I have done, for different values of V, I have solved the transcendental equation corresponding to LP01 mode and obtained the values of B. After having obtained the values of B for different values of V, then I have plotted this and then numerically differentiated this BV with V, and then by numerical differentiation I have obtained this. Okay. So, this I refer to as exact variations, okay, that is by exactly solving the transcendental equations. Now, I also know that there is an empirical relationship between B and V, and that empirical relationship is given by this formula: B is equal to A minus B over V square, where A is this, B is this, and this relationship is valid in the range of V going from 1.5 to 2.5. From here, it is not difficult to obtain dBV over dV, which will come out to be A square minus B square over V square, and then V times d2 bV over dV square, which comes out to be 2B square over V square. So, from here I can, if I want to calculate the waveguide dispersion, then I can simply put 2B square over V square in place of this, and I can immediately get the waveguide dispersion. But how accurate it is, how accurate this empirical relationship is for obtaining waveguide dispersion. So, for that, what we have done here, I have plotted the variation of B as a function of V from empirical relationship, and then this and this obtained from empirical relationship also. Okay. So, I have plotted it here as red circles. So, these red circles show the variations of various terms with respect to V as obtained from empirical relationship. So, what I see that variation of B fits well, variations of dB over dV also fits quite well, but this term deviates quite a lot, except at a particular values of V which is close to 1.9. So, at around V is equal to 1.9, the agreement between the empirical relationship and the exact values is good, but when you deviate from this value, then they are the agreement is not good. Okay. So what should I do? Well, then I cannot use this for the entire range of V. Then Marcuse in 1979 gave another empirical formula which is much accurate, more accurate. It is again empirical relationship between V times d2 Vv over dV square and V, and the relationship is given by this. Okay. When I plot this, then which is shown here in green circles, then I find that this relationship fits very well in the entire range of V from 1.5 to 2.5. So, I can safely use this relationship for calculating waveguide dispersion in a single mode fiber. Now, let us look at an example. Take a typical conventional single mode fiber whose parameters are given by this, and this I have adapted from the textbook Introduction to Fiber Optics. So, for these values of fiber parameters, if I calculate the value of V, then the value of V comes out to be 2746.3 nanometer divided by lambda naught. Okay. So, when I put lambda naught in nanometers, then for that value of lambda naught I can find out the value of V, and these two values of N1 and N2 correspond to delta, which is about 0.27%. Now, let me analyze this and calculate all the dispersions and analyze this fiber. Okay. So, I analyze this fiber at 3 different wavelengths by calculating various parameters. So, when I put lambda naught is equal to 1100 nanometer, then V is 2.497. So, it is close to single mode, okay, but it is not exactly single mode, and the waveguide dispersion, if I calculate, comes out to be minus 1.78 picoseconds per kilometer nanometer. Material dispersion is minus 23 picoseconds per kilometer nanometer, and total dispersion is about minus 25 picoseconds per kilometer nanometer. So, these are the values at 1100 nanometer wavelength. At 1300 nanometer wavelength, waveguide dispersion is minus 3.7, material dispersion is very low, plus 1.58, as we can expect, because this is fused silica glass fiber, and for fused silica glass fiber the zero dispersion wavelength is around 1270 nanometers. So, the total dispersion is minus 2.14 picoseconds per kilometer nanometers. Near to communication window at 1560 nanometer, waveguide dispersion is about minus 6 picoseconds per kilometer nanometers, while material dispersion is plus 22 picoseconds per kilometer nanometer. So, the total dispersion comes out to be about 16 picoseconds per kilometer nanometer. So, what I see in this fiber, that this fiber has very low dispersion of about minus 2 picoseconds per kilometer nanometers at 1300 nanometer wavelength, while it has plus 16 picoseconds per kilometer nanometer dispersion near the lowest loss wavelength. So, to have a much better picture and wider picture, I have plotted here dispersion as a function of wavelength in the range 1.1 micron to 1.7 micron. So, this green curve shows that This is waveguide dispersion, which is always negative. This red curve shows the material dispersion and this blue curve shows the total dispersion. Here we have calculated the total dispersion by adding the material dispersion and waveguide dispersion, which is not rigorously correct, but it is quite accurate when the dispersions are not very high. If the dispersions are, the values of dispersions are very high, then I should not just add the material dispersion and waveguide dispersion, and in fact what I should do while calculating waveguide dispersion, I should also take into account the variation of n1 and n2 with respect to lambda. So, I should automatically include material dispersion while calculating waveguide dispersion. That would be much more rigorous analysis, but for small values of dispersion like this, if I just add them up, then it is sufficient. So, this is what I have. What is the meaning of negative dispersion and positive dispersion? We have seen that in material dispersion also, that for the wavelengths which are less than 1.27 micrometer, the dispersion is negative, material dispersion is negative. For the wavelengths longer than 1.27 micrometer, the material dispersion is positive, and waveguide dispersion is always negative. Okay. So, the total dispersion, what I see, is now shifted from 1.27, which is 0 material dispersion wavelength, from 1.27 micrometer to about 1.3 micrometer. So, I have 1.3 micrometer near 0 total dispersion wavelength. Okay. So, in the next lecture we would see what is the meaning of negative and positive dispersion, how various fiber parameters affect waveguide dispersion, how we can tailor the dispersion in a fiber by having different profiles. Thank you.